Hey there. Today we're going to be doing a challenge on on setting CPU and memory usage limits on Linux processes. So we'll learn a little bit about C groups, and we're going to do this hands-on. My goal is to learn something and to get some hands-on experience doing Linux troubleshooting and Linux exploring. And hopefully we can get through this challenge in this video. It is labeled as easy, but there are more challenges that build upon it. So I think this is going to be a good start for me, and I hope you enjoy it. So here we go. Let's see what we have. We are on an Ubuntu 24 virtual machine. And let's go ahead and start. So it says, in this basic challenge, you will need to start a Linux process while limiting its CPU and memory usage. The binary you will run is called OmniHog, a simple resource hog program that consumes all available CPU and memory resources when started. Run it in a C group with a CPU limit of 10% and a memory limit of 500 megabytes. So it's called OmniHog. And there it is. I'm curious if it's just a bash file and what it looks like. No, it's not a bash script. I guess it's a binary. Yeah, I think it's a binary. Okay. So cool. So I don't know how to create a C group, so I need to learn how to do that. I'm going to go ahead and just click on the first hint, and let me expand this beautiful diagram. If you've never worked with C groups before, check out this step-by-step guide, Controlling Process Resources with Linux C groups. Okay, let's go ahead and pop that open. Split the screen over here. All right, cool. So, controlling process resources with Linux control groups. Not a comprehensive guide, but a practical example of how to limit process CPU and RAM consumption using Linux C groups. The technique may be used to protect the system from particularly resource-hungry processes like OmniHog, ensure fair resource distribution among multiple applications, test applications performance under constrained resources. That's a good use case I didn't really think of, but yeah. Guarantee resource availability in multi-tenant environments. All right, so if you're very confused, that's okay. C groups called control groups. I'm familiar with them because they are one of the Linux primitives that are used to implement containers. And they basically will allow you to set memory and CPU limits for a given process, and super helpful for security reasons, for performance reasons, and the stuff that I just read right here. So let's see. We'll start with creating, configuring, and adding a process to a C group using the most basic and labor-intensive method, manipulating the virtual file system C group FS. Interesting. Okay. After that, we will see how exactly the same can be done using higher level tools like libcgroups, cgcreate, and cgexec, or systemd's systemd-run and slice units. While the focus will be on Linux native ways of controlling process resources, the covered techniques will also directly applicable to managing resources of containers and pods. So the tutorial is highly relevant for people practicing Docker and Kubernetes. Great. So just take a look at this diagram here. Version check. Maybe we should run that. So we'll do mount-l, and let's grep for C group. Okay, so we have so mount will show which file systems are mounted on the machine. And in this case, we have one called cgroup2. but it's actually a virtual file system based on what we just read, and not sure exactly what that means, but we are just checking the version here. So cgroup 2. So here's cgroup hierarchy. So control group slash has a dot slice, init.scope, user slice, session. So all these are C groups. I don't know. There's something about slices. I'm not sure what that is. A typical C group tree on a Linux host with systemd. So there's a C group tree. Okay. Here are some of those commands that were mentioned and C group operations. So let's try this ls command over here. So we'll do ls-l/sys fs C group. I just want to see that level. Let's make this a little bigger. Okay. It's saying new C group, but we don't actually. I guess when you make a new C group, it creates a directory in sysfs C group. I'm not sure what C groups we actually have available, but I see like these slices and scope. All right, let's just I'm confused. I'm still confused, but let's keep poking around here. cgroup.controllers, events, freeze, max depth. Okay, this is all the stuff I'm seeing over here. These are limit controllers available in child C groups, echo plus CPU IO into C group subtree control. Let's see if we can cat sys fs C group dot subtree control CPU memory PIDs. See if we can cat anything else. Controllers. Looks pretty empty. I don't know if we have any C groups defined here yet. Let's keep moving on. So create a C group and add a process to it. So we actually make a directory. We just echo in the values. And they say everything's a file on Linux. I don't know if that's exactly true, but they were basically putting values inside of files on a virtual file system. And I'm guessing kernel reads that, and somehow this is how we're setting the memory max. And this looks like maybe the number of, C groups are set on processes, right? So I don't know what cgroups.procs is. Whoa. Well, okay, so I guess 1, 2, 3, 4 in this example is the process ID of some process that we want to put a C group on. Oh, so we're just appending that to cgroups.procs, which I think is the processes on the machine that have a C group associated with them. So maybe we do. Let's look at this process here. So if we do a cat proc that command line, maybe that doesn't exist. That might have been a ephemeral process. No? Okay. Let's try this one. Com. Oh, okay. Com. Oh, these are kernel processes. Okay. Still confused, but let's move on. All right, let me zoom out of here. Real quick, what is a C group? From the man page, control groups, usually referred to as C groups, are a Linux kernel feature which allow processes to be organized into hierarchical groups whose usage of various types of resources can then be limited and monitored. Allow processes to be organized into hierarchical groups. Those might be the slices, I'm thinking, whose usage of various types of resources, CPU and memory, can then be limited and monitored. The only kernel's C group interfaces a pseudo file system called cgroup.fs. I was calling it a virtual file system, but maybe the correct term is pseudo file system. There is no dedicated system calls to create, modify, or delete C groups. Okay, interesting. So that's why you have to do something like echoing a value into a file, because you can't make a system call like you can when you're opening or reading a file. All C group manipulation is done through creating folders and writing to specially named files in the C group pseudo file system. On modern Linux distros, the pseudo file system is usually mounted at sysfs group. So we've been there, we've been exploring that. Already did this stuff. Okay, so creating a subfolder in cgroup.fs leads to a new C group creation. All right, so let's actually make our first C group. So we're going to do a make dir sysfs C group, and we'll call it my_C group. And we can't do that. So I'm actually just going to switch to root, or I'll just do sudo. Okay, cool. So we just created a C group. The folder gets automatically populated with a set of files that can be used to configure the new C group. Okay, let's check it out. All right, so when we made that directory, it actually generated a bunch of files within it. So maybe that's why it's called a pseudo file system, because that's typically not how file systems act. Like, they just do the operation that you said, like make a directory. This is actually doing more than that. Okay, so we have all those files. The exact set of files depends on the enabled controllers, which you can see in the cgroup.controllers file. Let's check it out. I'm just going to go into this directory, cgroup.controllers. CPU set, CPU, memory, huge table, PIDs. I guess these are controllers. Oh, maybe these are the types of resources that you can limit. Not sure what huge TLB is, or what's the difference between CPU set and CPU. Okay. Since C groups are managed by pseudo file system, folders and files granting write access to a certain folder or its file can be used to allow non-root users to configure C groups, including child C group creation. If the set of available controllers for a child C group needs to be further restricted, it can be done by writing to the parent's C group subtree control file. So here they are echoing plus CPU plus memory minus IO into the parent cgroup.subtree control. This is called cgroup delegation, linking to kernel documentation. We don't need to get all into that right now. the set of available controllers for a child C group needs to be further restricted. Okay, so in this case, we're saying for the child C groups, only control CPU and memory, not IO. I don't know. Anyways, there's ways you can control which controllers are being used. Higher level tools like these are merely wrappers performing make, dir, write, and the like calls on the C group FS subtree. That would be a pretty cool program to rewrite if I wanted to get a little more involved. That would be kind of a fun project to recreate one of these programs. If they're just wrappers, probably not that complex. Now let's get our hands dirty and run some experiments using an improvised resource hog program. Here's the source code that I was looking for earlier. It's a Go program. It says allocating chunks in 10 megabytes every second. Not super interesting to me right now, but basically it just uses a whole bunch of memory. Configuring a C group inside C group FS. First, let's create a new C group by making a directory. Okay, so I just made one called my C group, but let's make the other one following these instructions. So I'm already in sysfs C group, so I'll do a make dir hog _ pen. Sudo that. Okay. Oh, it does a little check. Okay. Yeah, I'm not doing this playground. I'm over in the challenge here, so that's fine. Next we'll set limits on CPU and memory usage. Let's say we want to limit the CPU usage to 50% and the memory usage to 100. Okay, so this is how you limit the CPU and memory usage. You just write this into CPU max. So we're limiting CPU usage to 50% and the memory usage to 100 megabytes. So for CPU, we'll write the CPU quota and the CPU period values to the. So yeah, it's 50,000 to 100,000. So I guess, I don't know. The CPU is sliced into 100,000 slices. So we're going to limit this, create a control group that limits the CPU to 50%. And then later on, we're going to apply this control group to that memory hog process. So let's set that CPU limit now. We're going to echo 50,000 and space 100,000 into hogpen CPU max. And that's not an append, it's just writing it directly in there. Let me just switch to root and we'll go into our hogpen control group, cat CPU max. Oh, it says it right there, max 100,000. Okay, cool. So let's try that again. Echo 50,000, 100,000 into CPU max. Okay, that set the CPU max. And then here 50,000 is the maximum. On multi-core systems, the maximum CPU usage can be above 100%. For instance, on a machine with 2 cores, specifying 200,000, 100,000 is perfectly valid. That's good to know, considering there's hardly any CPUs with just a single core. So to limit memory usage, it's probably very similar. So if we do a cat on memory max, it just says max. So we're going to echo 100m into memory.max. All good. Oh, wow. It actually converted that to bytes, I think. That's pretty cool. Okay. Now let's start the resource hungry process. So let's exit out of our root and we'll go to our home directory. Oh, yeah, we are a little bit confusing. We're in the challenge lab over here. This is the, just like some guide. So I don't have that file, but basically if we go back over here, let's see what our challenge is that we have this OmniHog, right? And we want to, first we need to create our C group and then associate it with that process. So let's go ahead and create the C group now that we know how to do that. So I'm actually going to switch to root again. And we'll go to /sys fs C group. And we'll make our C group, it doesn't specify a name. Let's just call it, OmniHog. And we'll go into OmniHog. We should see all these files populated, right? Great. So if we cat CPU max, the max is 100,000 here. So we'll just echo, we want 10% CPU. So that's going to be 10,000, 100,000 into CPU max. And then for memory, we're limiting it to 500 megabytes. So we'll echo 500m into memory.max. Cat memory.max. There we go. And just to verify, CPU.max. Cool. Okay, so we have our C group. Now, we're going to go back over to our guide here that's telling us how to associate it with a process, right? Oh, I guess we're probably just going to be echoing the process ID into this. Because if we switch over here, we ls inside of our control group and we cat cgroup.procs, probably nothing, right? Yeah. So what they did here was they run hog, it starts the process, then they get the process ID using pgrep, and then they echo that into the procs. And then when a process running in a C group hits the memory limit, there's an OOM event that causes the process termination. So I think what we will probably do is start up OmniHog, get the PID, echo it into cgroup.procs, and then it should receive an OOM after some time. So let's go ahead and we'll just do a PS and make sure OmniHog isn't running. We'll grep for Omni. Okay, nothing there. So we'll do a OmniHog. I guess we probably want to run that in the background. So we can just do an OmniHog and then we'll do a PSOX. It's still running, but basically here's our process ID for OmniHog. I actually need to get, I'll probably just open another terminal. Let's switch to root, and we'll go to sys fs cgroup omni. Okay, so we have our process ID. We're going to echo that into, and actually we'll append that, even though there's nothing in there. I think that's what we generally would want to do. And procs. All right, so over here, oh, we did it. Okay. But I do want to see this process get killed, don't you? So it doesn't look like the screen's moving, but it actually is. And if we do just a ps-ox and grep for omni, we'll see 11.037 is still running. If we look at top, we can probably see OmniHog up there using a lot of memory. So I'm guessing in a little bit, we're going to see this process get killed. So let's try to remember there's 11.037. And then while that's running, I'm just going to go over here and oh, yeah, I think it just got killed, perhaps. Maybe not. Let's see. Nope, still running. Okay, but let's see if we can just kind of summarize, wrap things up over here. It's kind of interesting to me that like you have to start a process first and before you put it inside of a C group, so to speak. When a process running in a C group, wait, hold on. So we ran OmniHog, it's not yet constrained by the C group. We move it to the C group. All you need to do is write its PID to that file. So we did that. When a process running in a C group with a memory limit approaches that limit, an out-of-memory event is triggered. Adding an already running process to a C group by writing its PID is handy, but it doesn't work if you want to ensure that the process resource consumption is limited at all times. Right, because what about that time before you actually write the PID into this file? Like it could be exceeding its limit without leaving even a short gap between the process starting and being added to the C group. Luckily, when a process is started, it inherits the C group of its parent process. So you can move the parent process to the required C group and then make it start the already limited child process. What? When a process is started, it inherits the C group of its parent process. So in this case, it was bash was the parent process. Oh, by the way, it's killed. I'm just looking over here. I think, hold on, let me get out of top and look at Omni. Okay, yeah, it was killed. And maybe we could even, I don't know, journal CTL. I don't know all the flags here, but we might get, yep, there we go. Towards the bottom, I see an kill. Memory C group out of memory killed process 1137 OmniHog. Beautiful. So that's a log from the kernel. And it looks like, yep, here's the process ID. Looks like total VM. I don't know if that's virtual memory or what, but resident set size. So yeah, it did a little stat on it and then killed it. Pretty sweet. Let's go back over here. So yeah, the thing about the child process, parent process is kind of strange. When a process is started, it inherits the C group of its parent process, so you can move the parent process to the required C group and then make it start the already limited child process. So if we wanted to do that, we would have to put bash inside of a C group with the same limits that we want OmniHog to use. Like, that doesn't really make a lot of sense to me. To demonstrate this, let's move the current shell process to the hog pen group. So echo $$, pretty sure that's... Actually, what does that mean? Is that the parent process ID? This is the process. This is just the process ID, I guess, of whatever process is running. Okay. And interesting though that when we first did this, it also printed OmniHog, which would have been a child process of bash. So if we run OmniHog again, and then over here, we do an echo PID. Oh, this is a different bash session though. Okay, let me kill this, run it again in the background, boom, and then do a echo $$. So we get 9736. We do a PS aux. I just killed it. PS aux grab 9376. What was it? 9736. Sorry, I'm getting a little bit into the weeds, but this is how I like to learn, my friends. So that's our bash process. Interesting how it reported that child process though. Anyways, so what is this doing? Let's move the current shell process into the hog pen C group. And then start the hog process. Finally, when the C group is no longer needed, it can be removed using removedir. Notice that you won't be able to remove the C group if there are still processes inside it. So you have to wait for the hog process to get killed and also exit the shell session that you moved. We can try that. I mean, this should fail if we do a removedir on sys fs C group omni. Whoop. Was that not running? It seemed to work. No, it's not there. But don't we have OmniHog running? Yeah. And did we not? Yeah, we didn't put that in the cgroup.pids. Okay. Anyways, I'm going to take that with a grain of salt. Or not a grain of salt, but I'm going to take that as true here. That you can't remove the C group directory if there's a process running in it that's part of the C group. The thing about the parent process though, let me just read that again because I'm not really grokking this. Luckily, when a process is started, it inherits the C group of its parent process, so you can move the parent process to the required C group and then make it start the already. So I'm trying to think of how Docker and Podman and how they actually implement C groups, implement containers with C groups. And I guess there's some initial process that acts as the default C group. I mean, there's got to be a default C group. because it doesn't make sense to me to, you start up a process, so that, say like Docker runs a container and then echoes the container process ID into the C group. That doesn't seem right. So there's probably some initial, it's probably just inheriting from the parent process. Anyways, that was pretty cool. I think there's more. Okay, so I'm not gonna go on. It's already nearly 40 minutes into this, but we just created a C group, and we restrained a process, so that way that OmniHog doesn't take up all the memory on the machine and crash other processes running on it. We set the C group. That was pretty sweet. We saw that it worked, saw the logs in journalctl from the kernel, and this was a good learning experience. I hope you enjoyed it. Shout outs to you if you're like, watch the whole thing. That's wild. But if you have any questions or tips, please leave it in the comments, and I'll see you next time.